Look up at the night sky, and you'll see a familiar tapestry of stars. But what if I told you that beyond that peaceful glitter lies a universe of chaos, wonder, and mystery? We've sent telescopes beyond our atmosphere, mapped galaxies millions of light years away, and yet some of the most breathtaking structures in the cosmos defy everything we think we know. From vast cosmic rings that shouldn't exist to eerie voids where galaxies simply vanish, space is filled with formations so strange, so beautifully perplexing, that they keep astronomers awake at night questioning the very laws of physics. What are these enigmatic shapes, and why do they challenge our most fundamental ideas about how the universe works? Today, we're setting off on a journey far beyond our solar system, beyond the Milky Way, and into the deepest corners of observable space to explore 25 of the most head-scratching, imagination-defying galactic structures ever discovered. These are not just cosmic accidents, they're clues, pieces of a puzzle we're only beginning to assemble. Some look like celestial fingerprints left by forces we can't yet see. Others resemble vast architectural marvels built on a scale so immense it's almost impossible to fathom. Each one tells a story of creation, destruction, and mysteries that rewrite the textbooks. You're about to witness formations that bend light, distort time, and hum with energies we can scarcely measure. This isn't just a tour of beautiful anomalies, it's an invitation to rethink reality itself. As we voyage through these 25 puzzling galactic structures, remember, you're not just a spectator. You're part of the curiosity, the wonder, and the relentless human drive to understand the cosmos. So let's begin. Our journey begins close to home, at least in cosmic terms, with a structure so immense it forced astronomers to reconsider one of their most fundamental beliefs about the universe. Imagine, if you can, a wall, but this isn't a wall built of brick or stone. It's a wall constructed from galaxies, a vast filament of galaxy clusters, superclusters, and immense cosmic voids. Now hold that image in your mind and try to grasp its scale. This structure, known as the Hercules-Corona Borealis Great Wall, stretches for an almost incomprehensible 10 billion light-years. To put that in perspective, the entire observable universe is about 93 billion light-years across. This single structure, this one cosmic formation, takes up more than a tenth of everything we can see. Its discovery in 2013 didn't just break records, it sent shockwaves through the field of cosmology. The reason for this upheaval lies in a cornerstone of modern astronomy called the cosmological principle. This principle essentially states that on a large enough scale, the universe is homogeneous and isotropic. In simpler terms, it should look roughly the same in every direction, and no one place should be significantly different from any other. Matter should be distributed fairly evenly. The Hercules-Corona Borealis Great Wall is a direct contradiction to that idea. It represents a staggering concentration of matter, a colossal irregularity in the fabric of the cosmos. Finding something this huge is like looking at a vast, calm ocean and suddenly seeing a single wave that's 1,000 miles high. It simply shouldn't be there according to our established models. This isn't just an abstract puzzle for theorists. The existence of such a massive structure challenges our understanding of the universe's very evolution. The current models of the Big Bang and the subsequent inflation of the universe set a theoretical limit on how large any structure can grow, based on the age of the universe and the speed at which gravity can pull matter together. The Great Wall vastly exceeds that limit. It's too big, too massive, and too coherent to have formed in the time the universe has existed under our current understanding. So its presence forces us to ask profound questions. Did the universe evolve differently than we thought? Are there forces or processes at work on the largest scales that we haven't yet accounted for? Or does this mean we need to fundamentally revise our theories of cosmic evolution? The Hercules-Corona Borealis Great Wall stands as a silent, colossal monument to the fact that the universe still has profound secrets to reveal. Yet as colossal as the Hercules-Corona Borealis Great Wall appears, it was not the first structure to shake the foundations of modern cosmology. That honor goes to another, slightly closer and equally baffling formation, discovered over a decade earlier. Just as one monumental wall forces us to reconsider the rules, another invites us to look closer at the intricate architecture of the cosmos itself. This brings us to our second structure, the Sloan Great Wall. Discovered in 2003 by astronomers working on the Sloan Digital Sky Survey, this structure is a breathtaking filament of galaxies, a sprawling cosmic river system that stretches for an astonishing 1.37 billion light-years. To grasp that distance, consider a trip across it at the speed of light. Even at that impossible velocity, a photon would need to travel for over 1,370,000,000 years to go from one end to the other. It's a structure of such grandeur that it held the title of the largest known structure in the universe for several years, a true titan of the cosmos. The Sloan Great Wall isn't just a random clumping of matter, it's a specific type of formation known as a galaxy filament. These are the backbone of the cosmic web, the largest known arrangements of matter in the universe. Think of the universe not as a scattered collection of galaxies, but as a vast, three-dimensional spiderweb. The dense threads of that web are these filaments, where galaxies and massive clusters are woven together by gravity, and the great empty spaces between them are the cosmic voids. The Sloan Great Wall is one of the thickest, most prominent threads in that entire web, a superhighway of star systems on a scale that is almost impossible for the human mind to comprehend. Its initial discovery, however, posed a serious problem. While not violating the cosmological principle to the same extreme degree as its larger successor, the Sloan Great Wall's immense size and coherence presented a significant challenge to the standard model of cosmology at the time. The models predicted that while structures would form, there was a statistical limit to how large they could grow. The Sloan Wall seemed to push right up against that limit, and for a time many wondered if it had exceeded it. It became a key piece of evidence in a heated debate among cosmologists, forcing refinements in our simulations of how gravity shapes the universe over billions of years. It demonstrated that the cosmic web was far more complex and organized on larger scales than our theories had initially predicted. The existence of the Sloan Great Wall and others like it teaches us a profound lesson about the universe's structure. It shows us that the cosmos is not merely random. It possesses an architecture, a grand design governed by the relentless force of gravity. Each of these galaxy walls is a testament to the slow, patient work of gravity pulling matter together over eons, creating patterns in the darkness. By studying its detailed map, the specific arrangement of its galaxy clusters, and the voids it borders, astronomers can work backwards, piecing together the history of how our universe assembled itself. It acts as a cosmic fossil, preserving the conditions of the early universe and providing critical clues about the nature of dark matter and dark energy, the mysterious forces that ultimately dictate how this vast web evolves. But if these vast walls represent the universe's largest-scale architecture, our next structure reveals a beauty of an entirely different kind, one not of immense scale but of perfect, almost impossible symmetry. From the grand tapestry of the cosmic web, we now turn our gaze to a single, breathtaking galactic island so unique it stands alone in its perfection, Hoag's object. Discovered in 1950 by astronomer Hoag, this celestial wonder appears less like a typical galaxy and more like a massive, cosmic eye staring back at us from the depths of space. At its center lies a dense, brilliant core of aging yellow stars, glowing with a warm, familiar light. Surrounding this core is a stunning, perfectly circular ring of vibrant blue stars, young and hot, shining with the energy of recent birth. And between these two distinct populations lies a gap, a dark, seemingly empty void that cleanly separates the old from the new. It is a structure of such precise geometry that it looks almost artificial, as if crafted by some incomprehensible intelligence rather than the chaotic forces of nature. The mystery of Hoag's object lies in its formation. How does a galaxy achieve such a perfectly balanced, ringed structure? The most intuitive theory points to a galactic collision. We know that when a smaller galaxy pierces the heart of a larger disk galaxy, it can send ripples of density waves through the stars and gas, much like a pebble dropped in a pond. These waves can trigger massive bursts of star formation in a circular ring, which is exactly what we see in known ring galaxies. The problem is, there is no visible remnant of a perpetrator galaxy, no obvious culprit left behind in the vast gap between the core and the ring. The scene appears pristine, offering no evidence of a recent cosmic crash. This has led astronomers to explore other, more subtle possibilities, such as the concept of resonance. In this scenario, the rotating disk of the original galaxy could have developed instabilities, areas where gravitational forces naturally amplify and collect gas and dust. Over time, these resonant areas could have organized into a distinct ring where star formation ignited, while the central core remained undisturbed. It's a quieter, more serene theory of birth, one that doesn't require a violent encounter but instead relies on the innate music of orbital mechanics. However, this too presents challenges, as the flawless circle and the clean separation are exceptionally rare and difficult for resonance models to replicate so perfectly. What makes Hoag's object even more fascinating is that it isn't entirely alone. Peering deep into that dark gap between the ring and the core, astronomers have spotted another, more distant ring galaxy, a perfect loop of stars faintly visible in the void. This suggests that such formations, while incredibly rare, might be a recurring motif in the universe, a specific and beautiful outcome of galactic evolution that we are only just beginning to understand. It serves as a powerful reminder that the cosmos is capable of producing not only immense structures of chaos, but also ones of breathtaking order and elegance. If the vast cosmic walls and perfect rings represent an abundance of structure, our next destination is defined by a profound and unsettling lack of it. We now venture into one of the universe's most desolate places, a region so empty it has earned the dramatic nickname the Great Nothing. This is the Boötes Void, and discovering it was like finding a bottomless pit in an ocean of stars. Imagine a sphere of space so enormous that it could easily contain several thousand galaxies like our Milky Way. Now, imagine that within this colossal volume, you find only a handful of galaxies, 60 or so, where models and statistics predict there should be nearly 10,000. This is the reality of the Boötes Void, stretching an incredible 330 million light-years across. It is a spherical region of near-total emptiness, a gaping hole in the cosmic web that defies our expectations of how matter is distributed. Its discovery in the 1980s was a complete accident. Astronomers were conducting a large-scale redshift survey, meticulously mapping the distances to galaxies to create a three-dimensional picture of the universe when they stumbled upon this staggering nothingness. At first, they assumed it was an error in their data or their equipment, but repeated observations confirmed the impossible. A volume of space, nearly 1% of the entire observable universe, that was almost completely vacant. The existence of such a vast void presents a major puzzle for cosmologists. The prevailing Big Bang theory, with its inflationary model, does allow for irregularities regions that are slightly denser or slightly emptier than average. Gravity then amplifies these tiny fluctuations over billions of years, pulling matter into the dense regions to form galaxies and clusters, while the emptier regions expand into voids. But the scale of the Boötes Void is extreme. It is far larger and far emptier than our best simulations of cosmic evolution tend to produce. It's an outlier of such magnitude that it forces us to question whether our models of the early universe are missing a crucial piece of the puzzle. Perhaps the initial seeds of inflation were not as uniform as we believe, or maybe a strange interaction with dark energy has accelerated this void's expansion to an unnatural degree. What makes the void even more fascinating are the few lonely galaxies that do call it home. These isolated island universes, like the spiral galaxy MCG plus 0534-066, are the intrepid explorers of this cosmic desert. Studying them provides unique clues. For instance, these galaxies appear to be unusually rich in gas and are forming stars at a rapid rate. This makes a strange kind of sense, isolated from the gravitational tug of war and violent mergers that define life in a dense cluster. These galaxies can quietly and efficiently convert their pristine gas reserves into new stars without interruption. They are living fossils preserving a quieter, more isolated mode of galactic life that is almost impossible to study anywhere else. The Boötes void, therefore, is not truly nothing. It is a laboratory. It offers us a rare glimpse into the other side of cosmic evolution, not the construction of great walls, but the creation of great emptiness. By studying its profound lack of structure, we learn just as much about the forces that shape our universe as we do from its most magnificent formations. It stands as a stark reminder that the cosmos is a tapestry woven from both thread and empty space, and that the voids are just as important as the galaxies in defining its ultimate structure and fate. But for all the vast emptiness of the Boötes void and the perfect geometry of Hoag's object, some of the most startling cosmic mysteries aren't found in the far distant depths of space. They're right here in our own galactic backyard, hidden in plain sight until very recently. This brings us to a discovery that proves we still have much to learn about our home galaxy, the Milky Way. We now turn our attention to a pair of colossal, invisible structures that tower over our entire galactic disk, the Fermi Bubbles. Imagine two enormous orbs, one positioned directly above and one directly below the flat plane of our galaxy. These are not made of stars or gas that we can see with ordinary light. Instead, they are vast, hourglass-shaped structures of extremely hot gas and high-energy radiation, emitting powerful gamma rays. They are truly immense, each stretching an astonishing 25,000 light-years from the galactic center. To grasp that scale, consider that our entire solar system is located about 27,000 light-years from that same center. This means one of these bubbles extends from the heart of the Milky Way to a point in space that is almost as far out as we are. They are a defining feature of our galaxy's architecture, and yet we had no idea they existed until the year 2010. Their discovery was a triumph of looking at the universe in a different light, literally. The Fermi Gamma Ray Space Telescope, designed to scan the heavens for the most energetic form of light, provided a new map of the sky. When astronomers processed this data, they were stunned to find two massive, symmetrical lobes of gamma-ray emission bulging out from the galactic center. It was like using a special camera to suddenly see the massive, invisible pillars holding up a familiar building. These bubbles have very sharp, well-defined edges, suggesting they were created in a single, powerful event, a sudden and violent outburst of energy from the core of the Milky Way. So what could have created these titanic structures? The prime suspect is our galaxy's own supermassive black hole, Sagittarius A*. While it's relatively quiet today, the presence of the Fermi bubbles is compelling evidence that it wasn't always so peaceful. One leading theory suggests that in the relatively recent past, perhaps just a few million years ago, Sagittarius A* experienced a period of intense activity. A large cloud of gas or a star could have ventured too close and been torn apart, creating a tremendous accretion disk of superheated material. As this matter spiraled into the black hole, it would have generated unimaginable energy, ejecting twin jets of particles and radiation at nearly the speed of light perpendicular to the galactic plane. These jets would have blown enormous cavities in the halo gas surrounding the galaxy, inflating the bubbles we see today. But the black hole isn't the only potential culprit. Another plausible theory points to a frenetic burst of star formation near the galactic center. The core of the Milky Way is a crowded, dynamic place, and if a wave of hundreds or thousands of massive stars were born there simultaneously, they would live fast and die young. Their fierce stellar winds and their eventual deaths in spectacular supernova explosions would inject a tremendous amount of energy into their surroundings. This collective fury could have acted like a piston, driving a shock wave outwards that swept up material and carved out the bubbles. This stellar fireworks display could have been just as effective as a black hole eruption in creating these colossal structures. The true answer likely lies in a combination of these events, and studying the Fermi bubbles gives us a unique history lesson. By analyzing their size, shape, and the energy they contain, astronomers can essentially perform cosmic archaeology, working backwards to determine the timing and power of the cataclysm that created them. This event was a defining moment in our galaxy's life, a violent outburst that reshaped its immediate environment and funneled energy and matter far into the galactic halo. The bubbles are a permanent scar, a fossil record of a time when the quiet heart of the Milky Way roared with a force that echoed for tens of thousands of light years. And just as we ponder the immense energies that shaped our galaxy's core, we find another, far more delicate structure weaving its way through our galactic halo, a cosmic river of gas that tells a story of gravitational theft and a slow-motion merger happening right before our eyes. This is the Magellanic Stream, a breathtaking ribbon of neutral hydrogen gas that arcs across the sky, a faint but vast connection between our Milky Way and its two largest satellite galaxies, the Large and Small Magellanic Cloud. From our vantage point on Earth, this stream stretches over an incredible 180 degrees of the night sky. If our eyes could see in the wavelength of cold hydrogen gas, we would witness a colossal celestial bridge, a shimmering river of matter flowing from the Magellanic Clouds and pouring into the Milky Way's gravitational well. This isn't a static structure, it's dynamic, a testament to an ongoing interaction that has been playing out for billions of years. For astronomers, the stream is like a crime scene tape, outlining the gravitational struggle between a large galaxy and its smaller companions. The classic explanation for its formation is a tale of tidal forces, as the two smaller galaxies, bound together by their own gravity, have repeatedly swung around the much more massive Milky Way on their long orbital paths. Our galaxy's immense gravity has acted like a differential force. It pulls more strongly on the side of the clouds that is closer to us, effectively stretching them. Over many orbits, this gravitational tug-of-war has successfully stripped away vast amounts of gas, which has then been drawn out into the long, graceful stream we observe today. It's a process akin to the tidal forces that raise ocean tides on Earth, but amplified to a galactic scale over cosmic time. However, recent observations have added a fascinating layer of complexity to this story. While tides undoubtedly play the leading role, there's compelling evidence that another force is also at work: the pressure of the hot corona of gas that is believed to surround our galaxy. As the Magellanic Clouds plow through this thin, million-degree plasma, the resistance they encounter is like wading through water. This hydrodynamic pressure can also help to push and ram pressure strip gas out of the galaxies, contributing to the stream's formation and giving it its distinctive, swept-back appearance. It's likely a combination of these two powerful mechanisms, gravitational tides and hydrodynamic pressure, that sculpted this extraordinary feature. The Magellanic Stream is far more than just a beautiful cosmic accident. It is a live demonstration of how galaxies grow. This process, known as gas accretion, is fundamental. Large galaxies like our Milky Way cannot form all the stars they have from their initial gas supply alone. They must continuously replenish their star-forming fuel by cannibalizing smaller neighbors and siphoning off their gas. The stream is a direct pipeline, channeling pristine, metal-poor gas from the clouds directly into the halo of our galaxy. In the future, this gas will eventually rain down onto the galactic disk, providing the raw material for billions of new stars. We are witnessing our galaxy's dinner plate being filled, but the story doesn't end with the gas we can see. The real surprise hidden within the stream is what we can't see directly. Measurements of the stream's movement show that it is leading the motion of the Magellanic clouds themselves. This odd dynamic suggests the gravitational influence of something massive that is not emitting any light, a vast amount of dark matter. Astronomers now believe the entire Magellanic system, including the clouds and the stream, is enveloped in an enormous extended halo of dark matter. This dark matter gravity well is helping to shape the stream and hold it together as it journeys around our galaxy. The Magellanic Stream, therefore, is not just a river of gas, it is also a visible tracer, outlining the presence of an immense, invisible structure of dark matter, providing us with a unique and powerful tool to study this most mysterious component of our universe. Yet if the Magellanic Stream represents a river of matter flowing into our galaxy, our next destination reveals a powerful current pushing us away. We now venture beyond the familiar confines of our local group of galaxies to confront a staggering emptiness that is actively shaping our cosmic journey. This is the local void, a region of nothingness so vast and influential that its gravitational influence is literally repelling our entire galactic neighborhood. The local void is a truly staggering concept. It is a region of space bordering our own local group that spans an estimated 150 million light-years across. To put that incomprehensible scale into perspective, you could line up over 1,500 Milky Way galaxies end to end, and they would still not stretch across this abyss. It is one of the largest confirmed voids in our cosmic vicinity, a gaping hole in the universe's tapestry that begins practically on our galactic doorstep. For decades, this immense nothingness went unnoticed because it resides behind the plane of our own galaxy, its faint light obscured by the dust and stars of the Milky Way. It was a blind spot in our cosmic vision, hiding a profound secret. The true revelation about the local void isn't just its existence, but its active influence on us. Astronomers have meticulously mapped the motions of galaxies in our local universe, and a curious pattern emerged. While all galaxies are being carried along by the overall expansion of the universe, our local group, which includes the Milky Way, Andromeda, and dozens of smaller galaxies, is moving with an additional, peculiar velocity. We are traveling at a staggering 630,000 kilometers per hour in a specific direction relative to the cosmic microwave background. For years, the attractor pulling us was the focus, but a complete picture required understanding what is also pushing us. The answer lies in the void. This is where the story turns counterintuitive. We often think of gravity only as an attractive force pulling objects together. But in the context of cosmic structures, emptiness can exert a powerful repulsive effect. Imagine a vast region of space that is mostly empty. Because it has far less matter than the surrounding areas, it also has a much weaker gravitational pull. The denser regions of the universe, packed with galaxy clusters and superclusters, have a stronger gravitational attraction. The result is a cosmic tug of war where galaxies are not only pulled toward the dense regions, but are also effectively pushed away from the empty ones. It's not that the void is repelling us with some anti-gravity force. Rather, the stronger pull from the matter-rich areas on the other side wins out, creating a net motion that accelerates us away from the emptiness. The local void, with its profound lack of mass, is one of the primary engines behind this push. This discovery fundamentally changes our understanding of our place in the cosmos. We are not passive riders on the expanding fabric of the universe. We are actively being navigated by the gravitational landscape of our local environment. The push from the local void, combined with the pull from massive structures like the Shapley Supercluster far beyond it, creates the complex trajectory we are on. By studying this motion, cosmologists can essentially weigh the void. They can calculate how much mass isn't there by measuring how its absence affects the movement of the galaxies around it. This provides crucial, real-world data to test our models of how dark matter and dark energy influence the growth of these vast structures over time. The local void, an immense nothing, has become one of our most important tools for understanding the something that shapes the entire universe. Yet as we chart the immense gravitational push and pull of visible structures and cosmic voids, we are forced to acknowledge a far more pervasive and invisible architect shaping the cosmos. For every galaxy we see, for every cluster we map, there is an unseen skeleton holding it all together, a hidden framework of gravity that makes the universe as we know it even possible. This brings us to the most dominant yet most elusive structure in the entire universe, the dark matter halo. Picture a vast spherical cloud, but one that is utterly invisible. It emits no light, reflects no radiation, and interacts with ordinary matter only through the force of gravity. Now, imagine this cloud is colossal, extending far beyond the visible edges of a galaxy. For a spiral galaxy like our Milky Way, the familiar disk of stars and gas that we see in telescopes is just the bright, dense core at the heart of an immense, unseen sphere of dark matter that stretches for hundreds of thousands of light years. This is the dark matter halo. It is not a solid shell, but a diffuse, layered structure, densest at the center and gradually thinning out towards its edges. These halos are not rare, they are universal. Every galaxy, from the smallest dwarf to the largest elliptical, is believed to be embedded within one. In fact, it was the gravitational influence of these halos that allowed the first galaxies to form after the Big Bang, providing the necessary gravitational wells for normal matter to coalesce and eventually ignite into stars. The evidence for these invisible structures is overwhelming, yet it is all indirect, gathered by observing how they bend the fabric of spacetime itself. One of the most powerful methods is gravitational lensing, a dramatic confirmation of Einstein's theory of general relativity. When light from a distant galaxy travels through the universe, its path is straight unless it passes through a region warped by a massive object. A massive dark matter halo acts like a lens of curved spacetime, bending the light from galaxies behind it. This can create extraordinary visual effects, stretched arcs of light, multiple images of the same distant galaxy, or even perfect Einstein rings, a complete circle of light surrounding the invisible halo. By carefully analyzing these distorted images, astronomers can literally map the distribution of the unseen mass causing the distortion, creating a detailed picture of the halo's shape and density without ever seeing it directly. Another foundational piece of evidence comes from studying the motion of stars within galaxies, specifically their rotation curves. According to the laws of gravity, stars on the outer edges of a spiral galaxy should orbit more slowly than those near the bright center, much like planets in our solar system move more slowly the farther they are from the sun. But observations tell a completely different story. Stars and gas clouds at the very outskirts of galaxies orbit at the same high speed as those near the core. The only way this is possible is if the galaxy is surrounded by a massive, invisible sphere of matter, a dark matter halo whose gravity provides the extra pull to keep those outer stars whipping around at such incredible velocities. This rotation curve anomaly was one of the first and most powerful clues that the universe contained far more matter than we could see. Despite knowing they exist, the true nature of dark matter halos remains one of the deepest puzzles in all of science. We know they make up roughly 85% of all the matter in the universe, meaning everything we can see, every star, planet, and galaxy. is just the visible frosting on a much larger, invisible cake. But we still don't know what dark matter actually is. Is it a yet-to-be-discovered exotic particle like a WIMP, a weakly interacting massive particle? Or could it be something even more strange? The way these halos are distributed adds another layer of mystery. Our most sophisticated supercomputer simulations, which model the evolution of the universe with dark matter, produce halos that have a very specific cuspy structure. Their density increases sharply towards the center. However, observations of some smaller dwarf galaxies suggest their dark matter cores might be smoother and less dense than the simulations predict. This small-scale discrepancy hints that our understanding of dark matter's properties, or perhaps even our models of physics itself, might be incomplete. These halos are not just passive scaffolds, they are dynamic and integral to the story of every galaxy. They govern how galaxies form, how they merge with others, and ultimately how they evolve over billions of years. The dark matter halo is the true ruler of the cosmic realm, its invisible hand guiding the fate of all visible matter. And as we continue to probe these mysterious structures, we are not just searching for dark matter, we are searching for a fuller understanding of the fundamental architecture of reality itself. Just when we thought we had grasped the true scale of cosmic structures, the universe presents us with a curve on a scale so grand it seems to defy both logic and the very principles we hold dear. From the invisible embrace of dark matter halos, we now turn to a formation that is very much visible, a structure so vast and so elegantly simple in its shape that its discovery has sent a fresh wave of fascination and doubt through the world of cosmology. This is the giant arc, a celestial formation that stretches across the sky, challenging our understanding of the universe's architecture. Discovered in 2021 by astrophysicist Alexia Lopez while analyzing the light from distant quasars, the giant arc is a colossal assemblage of galaxies, galactic clusters, and intergalactic gas and dust. But it is its specific arrangement that makes it so extraordinary. These elements are not randomly scattered. They form a near-symmetrical, crescent-shaped structure that spans an astonishing 3.3 billion light-years. To comprehend that distance, consider a light beam setting off from one end of the arc. By the time it finally reached the other end, our entire solar system would have formed, evolved, and witnessed the rise and fall of the dinosaurs a dozen times over. It is a structure of almost unimaginable proportions, and it hangs in the distant universe, roughly 9.2 billion light-years away from Earth. The existence of such a structure presents a direct and profound challenge to the cosmological principle, one of the foundational pillars of modern astronomy. This principle states that when viewed on a sufficiently large scale, the universe should appear homogeneous and isotropic essentially, the same in every direction and uniform in its distribution of matter. There should be no preferred direction or location, and certainly no giant, recognizable shapes etched across billions of light-years. The giant arc, with its coherent and immense form, directly contradicts this. It is a glaring irregularity, a pattern in the cosmic fabric where none should exist. Finding a structure this large and this distinct is like looking at a vast, sandy beach and finding a single, perfect sandcastle that stretches for miles. According to our established models of the universe, it simply shouldn't be there. The implications of this discovery are immense. The theoretical limit for the size of a cosmic structure is set by something called the Barrian Acoustic Oscillation Scale, a standard ruler imprinted on the universe by sound waves in the primordial plasma after the Big Bang. This scale is about 1 billion light-years. The giant arc, at more than 3 times this size, completely shatters that expected limit. Its mere presence forces cosmologists to ask difficult questions. Does this mean our understanding of the universe's earliest moments is flawed? Could it be evidence of exotic physics or unknown forces that operated in the infant cosmos, imprinting these giant patterns on the distribution of matter before inflation even began? Or does it suggest that the universe is not homogeneous on the largest scales, meaning we might need to fundamentally reconsider our most basic assumptions about the cosmos? What makes the giant arc even more compelling is that it isn't an isolated anomaly. It exists in the same cosmic neighborhood as other enormous structures like the Sloan Great Wall and the Hercules-Corona Borealis Great Wall, suggesting that this particular region of space might be unusually rich in large-scale formations. This clustering of giants hints at an even deeper level of organization in the universe's large-scale structure, a pattern of patterns that we are only beginning to discern. It suggests that the cosmic web might have its own architecture, with threads and nodes on a scale we are only just becoming capable of measuring. Studying the giant arc is like looking at a fossil from the universe's childhood. Its size and shape preserve information about the conditions of the early cosmos. By mapping its detailed structure, the precise way galaxies and matter are distributed along its curve, astronomers can work backwards to test theories of how gravity and dark energy have shaped the universe over billions of years. It acts as a natural laboratory for understanding the tension between gravity, which wants to pull matter together into structures, and dark energy, which wants to push it apart. The arc's very existence shows that gravity has been winning on a scale we never thought possible. This immense structure, a graceful curve against the darkness, is more than just a list of galaxies. It is a question mark hanging in the void, compelling us to rethink everything we know about the universe's grand design. But if the giant arc challenges our view of the universe's fabric from a distance, our next destination brings the cosmic web into shockingly personal focus. We are about to discover that we are not just observers of these massive structures, we are residents of one. This brings us to the concept of galactic superclusters and to the revolutionary understanding of our own address within this vast architecture, the Laniakea Supercluster. For centuries, we located ourselves in the solar system, then in the Milky Way galaxy, and eventually within a small local group of galaxies. But the true scale of our neighborhood is far grander. Galaxies are not scattered randomly through space. They gather into clusters which themselves are bound together into even larger assemblies called superclusters. These are the continents of the cosmos, the largest gravitationally bound structures we know of, each containing the mass of 100,000 Milky Ways or more. They form the dense nodes and thick filaments of the cosmic web, and for a long time, mapping them was like trying to chart the boundaries of a continent while standing in one of its forests. We knew we were part of something larger, but its true shape and our place within it remained elusive. That all changed in 2014 with a groundbreaking new definition of our cosmic home. Using a sophisticated technique to map the peculiar velocities of thousands of galaxies, that is, their individual motions relative to the overall expansion of the universe, a team of astronomers was able to trace the flow of galaxies driven by gravity. They were essentially mapping the watershed of the cosmos. Just as water flows downhill into a common valley, galaxies flow along gravitational gradients toward the densest regions of mass. This work revealed the breathtaking expanse of the Laniakea Supercluster. Laniakea, a Hawaiian word meaning immense heaven, is a fitting name for a structure that spans 500 million light-years and contains approximately 100,000 galaxies, including our own Milky Way, the Andromeda Galaxy, and the entire Virgo cluster. Understanding Laniakea redefines our home. We are no longer just in the Virgo cluster. That cluster is merely a prominent part of the larger Laniakea. This supercluster has a clear center of gravity, a region known as the Great Attractor, towards which all the galaxies within Laniakea, including ours, are slowly drifting. It's not a dense, packed cluster, but a vast, river-like network of galactic groups and clusters all flowing along the same gravitational currents. The borders between superclusters are not walls, but the points where these cosmic watersheds divide. For instance, the galaxies on the far side of Laniakea are flowing toward a different attractor, marking the beginning of a neighboring supercluster, Perseus Pisces. The formation and evolution of a structure like Laniakea is a story written in dark matter. In the early universe, slight overdensities in the mysterious dark matter began to collapse under their own gravity, forming vast halos. These halos acted as gravitational seeds, pulling in ordinary baryonic matter, the gas that would eventually form stars and galaxies. Over billions of years, smaller halos merged into larger ones, and the galaxies within them followed suit, congregating into groups, then clusters, and finally, the immense filaments of a supercluster. The entire Laniakea Supercluster is still dynamically evolving today, its galaxies continuing their slow, inevitable dance toward the Great Attractor, a journey that will take billions of years to complete. This new, fluid definition of a supercluster, based on gravitational flow rather than just a static snapshot in space, is a paradigm shift in cosmology. It shows us that the universe is not a collection of static islands but a dynamic, flowing system on the grandest of scales. Laniakea is not the end of the story. It is merely one branch in an even larger cosmic structure. It is part of a vast filament that eventually connects to other superclusters like the Shapley Supercluster, the largest such structure in our local universe. By studying Laniakea, we are learning to read the subtle currents of gravity that sculpt the universe, tracing the invisible lines of dark matter that ultimately dictate the fate of all the bright galaxies we can see. Our home supercluster is a masterpiece of cosmic architecture, and we are only just beginning to understand our room within its immense halls. Yet as we map the grand superclusters and cosmic flows that define our local universe, we find that some of the most profound mysteries are written not in the light of galaxies, but in the faint, ancient glow that fills all of space, the cosmic microwave background. This afterglow of the Big Bang is the oldest light we can see, a snapshot of the universe when it was just 380,000 years old. And imprinted upon this otherwise remarkably uniform canvas is a peculiar, chilling anomaly that has sparked some of the most extraordinary theories in all of cosmology. This is the CMB Cold Spot, a cosmic bruise that just might be a window into realities beyond our own. Discovered in 2004 by NASA's Wilkinson Microwave Anisotropy Probe, the cold spot is not just a slightly cooler patch, it is a statistical outlier of stunning proportions. It spans a vast region of the sky, approximately 0.00015 radians across. To visualize that, hold your thumb out at arm's length. The area it covers is about the same size. Within this circle, the temperature of the cosmic microwave background is about 70 microkelvins colder than the average surrounding area. That might not sound like much, but in a universe that is otherwise incredibly smooth, with temperature fluctuations measured in mere millionths of a degree, this spot is a dramatic and unexpected deviation. It is a feature that, according to our standard models of the early universe, is exceptionally unlikely to exist by random chance alone. It stands out like a frozen fingerprint on the warm background of creation, and astronomers have been desperate to explain its origin. The most conventional and initially favored explanation was that this cold region was not a feature of the primordial universe at all, but rather a later stage illusion created by something called the integrated Sachs-Wolf effect. This complex-sounding phenomenon is actually a beautiful consequence of the universe's expansion. When light travels through a region of space that is still gathering mass, like a supercluster, it must climb out of a gravitational well. This costs it energy, stretching its wavelength and making it appear cooler, hence a cold spot in the CMB. Conversely, if light travels through a region that is losing mass relative to its surroundings, like a vast cosmic void, it gains energy as it exits, creating a subtle hot spot. The theory was simple. Perhaps the cold spot was simply the shadow cast by an immense void, a great cosmic nothingness between us and the CMB. If such a supervoid existed, It would provide a perfect physics-based explanation without requiring any new laws of nature. The hunt for this proposed supervoid began in earnest. Astronomers meticulously mapped the galaxy distribution in the direction of the cold spot, expecting to find a staggering emptiness. And they did find a void now known as the Eridanus supervoid. The problem is one of scale and significance. The Eridanus supervoid is large, but it is not nearly large enough or empty enough to account for the profound coldness observed. The measured temperature drop is simply too great for the size of the void we see. It would be like a small pothole causing a dip in the road as deep as a canyon. The numbers don't add up. While the void might be contributing to the effect, it cannot be the sole cause. This dead end forced cosmologists to consider far more radical ideas. With a mundane explanation failing to fully satisfy, the door was opened to the spectacular. The most tantalizing and controversial theory is that the cold spot is evidence of a collision with a parallel universe, a bruise left on our cosmos from an impact with another bubble universe in the vast multiverse. This idea springs from the theory of eternal inflation, which suggests our universe is just one bubble in a frothing, infinite sea of universes, each with its own distinct physical laws. In this model, these bubble universes can sometimes collide. If our universe had such an encounter in its very distant past, the energy released at the boundary of that collision could have subtly altered the density of matter in that region of space. This would have left an imprint on the cosmic microwave background that would appear to us billions of years later as an inexplicably large and cold spot. It is a hypothesis that is as breathtaking in its scope as it is daunting in its near impossibility to verify with our current technology. Whether a sign of the multiverse or a statistical fluke we don't yet understand, the cold spot remains one of the most compelling unsolved puzzles in modern cosmology. It serves as a powerful reminder that our most precise map of the infant universe still contains features that defy easy explanation. It challenges us to refine our theories, to build better telescopes, and to keep our minds open to possibilities that seem, at first glance, to belong to the realm of science fiction. This cold, silent patch on the sky is a siren call to explorers, a hint that the deepest secrets of existence might be hidden in the most subtle details of the ancient light that surrounds us all. But if the cold, silent mystery of the CMB represents the universe's infancy, our next destination showcases its most violent and explosive adulthood. We now turn from the subtle chill of primordial light to the raging, high-energy firestorms unleashed by the most powerful engines in the cosmos. This brings us to the colossal and dynamic structures known as radio galaxies, and to their most spectacular feature, the giant radio lobes that can dwarf the galaxies that created them. At the heart of every radio galaxy lies a supermassive black hole, but not a quiet one like our own Sagittarius, a star. This is a black hole in its most active, ferocious phase, gorging on a relentless diet of gas, dust, and even entire stars. As this tremendous amount of matter spirals inward at nearly the speed of light, it forms a superheated accretion disk, a whirlpool of plasma so energetic that it glows across the entire electromagnetic spectrum. But the true spectacle happens at the black hole's poles. Intense magnetic fields generated by the churning accretion disk act like the most powerful particle accelerator imaginable, funneling some of this infalling material into two narrow, opposing jets that blast out into intergalactic space at relativistic speeds, a significant fraction of the speed of light. These jets are beams of pure energy and charged particles, and they travel for hundreds of thousands, even millions, of light years before they finally slam into the thin gas that exists between galaxies. It is at the ends of these incredible journeys that the radio lobes are born. When these high-speed jets plow into the intergalactic medium, they hit a wall of resistance. They rapidly decelerate, and all that immense kinetic energy has to go somewhere. The result is a catastrophic and beautiful collision. the material in the jet piles up, inflating like a balloon and creating vast, billowing clouds of radio-emitting plasma on either side of the host galaxy. These are the radio lobes. They are often symmetrical, forming a dumbbell-like structure centered on the galaxy, and they can be so enormous that the galaxy itself appears as nothing more than a tiny speck at the center of a cosmic hourglass. The particles within these lobes, twisted by magnetic fields, emit synchrotron radiation, a type of light most prominent in the radio part of the spectrum, which gives these galaxies their name. To witness this phenomenon in all its chaotic glory, we need look no further than one of our closest and most dramatic neighbors, Centaurus A. Located a mere 12 million light-years away, Centaurus A is a cosmic wonderland for astronomers. Through an optical telescope, it appears as a bizarre, messy galaxy, dominated by a prominent and warped dark dust lane that cuts across its center, the telltale sign of a past galactic collision and merger. But when we point a radio telescope at it, the view is utterly transformed. The familiar lenticular galaxy is utterly engulfed by two gigantic radio lobes that stretch over 1 million light-years from end to end, making them larger than 20 entire Milky Way galaxies laid out in a row. These lobes are a testament to an ongoing eruption that has lasted for millions of years. The story of Centaurus A is a story of resurrection and renewed violence. Astronomers believe it was once a normal elliptical galaxy until it cannibalized a smaller spiral galaxy. This merger not only provided the fresh fuel, gas and dust to awaken the dormant black hole at its core, but also likely delivered the specific angular momentum that helped shape and power the jets. The resulting outburst created the spectacular lobes we see today, but Centaurus A holds another secret. Its jets are not perfectly straight. They appear twisted and distorted, and closer to the core, smaller secondary lobes can be found nested within the larger ones. This suggests that the black hole's activity is not a single continuous event, but rather occurs in fits and starts. The black hole engine sputters, shuts down for a time, and then roars back to life, often with its axis pointing in a slightly different direction, painting a new set of lobes over the fading remnants of the old. This makes Centaurus a living laboratory for studying the life cycle of active galactic nuclei, showing us that these eruptions are episodic and that a galaxy's most violent phases can be each Chinese letter reignited by fresh inflows of material. Studying these radio lobes provides far more than just a spectacular light show. It gives us crucial insight into how galaxies regulate their own growth and influence their environment. This process, known as AGN feedback, is now considered a cornerstone of galactic evolution. The incredible energy pumped into the lobes by the jets does not stay there forever. Eventually, this energy heats the surrounding intergalactic gas, preventing it from cooling and falling back into the galaxy to form new stars. In the most massive galaxies, this feedback can effectively shut down star formation, rendering the galaxy a quiet, red and dead elliptical. Furthermore, the lobes themselves act as enormous repositories of energy and magnetic fields, which they can release back into the cosmic web over billions of years, helping to shape the thermodynamic state of the entire cluster of galaxies the radio galaxy calls home. These magnificent structures are not just the aftermath of a black hole's fury. They are the governing forces that dictate the future of everything around them. But as we witness the explosive feedback of radio galaxies and the dynamic flows within Laniakea, we must zoom out even further to comprehend the true pinnacle of cosmic architecture. These superclusters are not isolated continents. They are connected, woven together into structures of such staggering scale that they redefine the word immense. This brings us to a formation so vast it encompasses entire superclusters within its embrace, the Pisces-Cetus supercluster complex. To even begin to visualize the Pisces-Cetus complex, we must first recalibrate our sense of scale. Imagine a single supercluster like Laniakea, a gravitational watershed 500 million light-years across containing 100,000 galaxies. Now, imagine a structure so colossal that it connects several such superclusters into a single, interconnected network of galaxy filaments. This is the Pisces-Cetus supercluster complex, a sprawling web of galactic matter that stretches for approximately 1 billion light-years through the cosmos. It is not a single, dense object but a grand cosmic metropolis, with superclusters acting as its bustling downtown hubs, and the thin filaments of galaxies between them serving as the sprawling suburban connectors. This complex is one of the largest known structures in the entire observable universe, a titan whose very existence pushes against the theoretical limits of what our cosmological models say is possible. The formation of such an enormous structure is a story written in the first moments of the universe and played out over billions of years. It begins with the tiniest quantum fluctuations in the fabric of space-time during the inflationary epoch, an instant after the Big Bang. These microscopic ripples were then stretched to astronomical sizes by the universe's rapid expansion, becoming the seeds for all future structure. Over eons, gravity acted on these seeds, relentlessly pulling dark matter and ordinary matter together. The Pisces-Cetus complex represents the culmination of this process on the very largest scales, a place where multiple, massive gravitational wells, the superclusters, have drawn matter into a connected network of unparalleled size. It is the ultimate expression of the cosmic web, a pattern of matter that traces the underlying, invisible scaffolding of dark matter that permeates everything. However, this grand scale presents a profound and unsettling challenge to our understanding of cosmic evolution. The problem is one of time. The universe is approximately 13.8 billion years old, and the speed at which structures can form is governed by the speed of gravity and the expansion rate of the universe. Cosmologists use sophisticated computer simulations to model this growth, and these models predict a statistical limit to how large coherent structures can become within the age of the universe. The Pisces-Cetus complex, with its billion light-year span, exists right on the edge of, and some argue beyond, this theoretical maximum size. It is a structure that, according to some calculations, shouldn't have had enough time to form. Its existence forces astronomers to ask difficult questions. Did structure formation begin earlier than we think? Could the influence of dark energy, which accelerates the expansion of the universe, have played a different role in the past? Or does this immense complex suggest that the initial fluctuations from the Big Bang were not as random as we believe, perhaps containing pre-existing patterns on scales we are only now beginning to see? Studying this complex is like looking at a living fossil from the dawn of time. Its sheer size means that the light we receive from its farthest reaches is incredibly ancient, offering a snapshot of the universe when it was much younger. By mapping the precise distribution of its galaxies and measuring their motions, cosmologists can work backwards to test the fundamental laws of gravity on scales never before possible. It serves as a natural laboratory for understanding the long-term battle between gravity, which wants to pull things together, and dark energy, which wants to push them apart. The very fact that gravity has managed to organize matter on the scale of the Pisces-Cetus complex tells us that its pull is incredibly potent, even across these mind-boggling distances. This vast network is more than just a collection of galaxies. It is a critical benchmark, a challenge to our models, and a guidepost pointing toward a deeper understanding of the forces that have shaped and continue to shape the entire cosmos. Yet for all the grand billion light-year architecture of the Pisces-Cetus complex, some of the most influential structures in shaping a galaxy's destiny are found not in the vast intergalactic voids, but right at the very heart of the galaxies themselves. We now turn from the cosmic web to the intricate dynamics within a single galaxy, to a feature so common and yet so pivotal that it dictates the very life cycle of stars. This brings us to the galactic bar, a massive, rigid structure of stars and gas that cuts through the center of a majority of spiral galaxies, including, we now believe, our very own Milky Way. Look at a classic spiral galaxy like the Pinwheel Galaxy, and you see a graceful, swirling pinwheel of arms. But now, look at a galaxy like NGC 1300, a stunning example captured by the Hubble Space Telescope. At its center, you don't see a soft, rounded bulge of stars. Instead, you see a bright, straight lane of light, a rigid bar, that cuts directly across the galactic core with the spiral arms seeming to unwind from its tips. This isn't a rare oddity, it's a dominant form. Astronomers estimate that up to 2/3 of all spiral galaxies in the local universe are barred spirals. This prevalence tells us that the bar is not a cosmic accident. It is a fundamental phase in the life story of a spiral galaxy, a natural engine that drives its evolution. The formation of a bar is a story of gravitational instability and cosmic resonance. A spiral galaxy is not a solid disk. It's a fluid, dynamic system of stars and gas all orbiting the center of mass. Imagine a perfectly symmetrical, smooth galaxy disk. Now, imagine a slight disturbance, a minor clumping of stars from a passing dwarf galaxy, or even the inherent unevenness in the disk's own rotation. This creates a subtle gravitational tug that can cause stars to shift from their circular orbits into more elliptical paths. If these new orbits begin to align and reinforce each other, a self-perpetuating wave, a standing density wave, can form. This wave doesn't move with the stars. It is a fixed pattern, a traffic jam in the stellar orbits that creates a permanent, rigid structure of densely packed stars, the bar. It's a natural outcome for a massive, rotating disk of stars, a sign of a galaxy maturing and settling into a stable but dynamic structure. Once formed, the bar becomes the primary engine driving the galaxy's evolution, acting as a massive gravitational mixer that funnels material inward. The bar's immense gravity exerts a constant torque on the gas clouds and dust lanes within the spiral arms. As these clouds orbit the galaxy, the bar's gravitational field pulls on them, slowing them down and robbing them of angular momentum. This loss of energy causes the gas to sink inward on a grand scale, channeling it from the outer disk directly toward the nuclear region of the galaxy. This inward flow is the bar's most crucial function. It is the primary mechanism for feeding the galactic center. This infalling gas can trigger intense bursts of new star formation, building up the central bulge of the galaxy. More dramatically, if enough gas reaches the very center, it can provide the fuel to awaken and feed the dormant supermassive black hole that resides there, potentially triggering an active galactic nucleus phase and dramatically altering the galaxy's future. This process, however, leads to a fascinating paradox that may ultimately spell the bar's own destruction. As the bar efficiently drains the inner disk of its gas and feeds the central black hole, it potentially starves itself of the very material that helps maintain its structure. Furthermore, the gas that piles up in the center can form its own, smaller structures like nuclear rings or nested bars, whose gravity can disrupt the stability of the primary bar. Over billions of years, this relentless transfer of angular momentum and the resulting buildup of mass in the core can cause the bar to weaken and eventually dissolve. This suggests that a strong bar might be a temporary, albeit long-lived, phase in a galaxy's life. A barred spiral could eventually evolve into a more common, featureless elliptical galaxy, its structure erased by the very processes it initiated. This life cycle raises a profound and lingering mystery. If bars are such a natural outcome for rotating disks, why do some seemingly identical spiral galaxies lack them? Why does our neighboring Andromeda galaxy possess a weak, boxy bar, while the Triangulum galaxy shows no clear sign of one at all? The answer likely lies in a galaxy's history and environment. A major merger or a close gravitational interaction with another galaxy can violently disrupt the delicate orbital resonances required to form and sustain a bar, effectively preventing one from ever taking shape. Alternatively, a galaxy that has already consumed most of its gas might not have enough material left to form a bar in the first place. The presence or absence of a bar is a clue to a galaxy's past, whether it lived a quiet, isolated life or one filled with dramatic encounters. The humble galactic bar, a simple straight line of stars, is therefore much more than a visual curiosity. It is the beating heart of a galaxy's metabolism, a catalyst for both creation and destruction, and a lasting record of the dynamic forces that shape galactic evolution over billions of years. But just as the galactic bar illustrates the complex dynamics within our own galaxy, a far larger and more controversial structure may be shaping our entire cosmic perspective from the outside in. This brings us to a proposed void of such staggering proportions that its existence, or lack thereof, could resolve one of the most heated debates in modern cosmology. This is the KBC void, a potential local supervoid that places our Milky Way at its center, challenging our most fundamental measurements of the universe itself. The story of the KBC void begins not with a direct observation, but with a persistent and troubling discrepancy known as the Hubble tension. In simple terms, astronomers have two primary ways to measure how fast the universe is expanding, a rate known as the Hubble constant. One method looks at the ancient universe using the cosmic microwave background as a standard ruler. The other method uses relatively nearby objects like pulsating stars called Cepheid variables and certain types of supernova as cosmic mile markers. The problem is these two methods give different answers. The local measurements suggest an expansion rate that is significantly faster than the prediction from the early universe. It's as if two incredibly precise clocks built by master craftsmen are ticking at different speeds and no one can figure out why. This tension implies a fundamental flaw in our understanding of physics, a potential crisis for the standard model of cosmology. In 2016, a team of astronomers led by Ryan Keenan, Amy Barger, and Lennox Cowie proposed a radical and elegant solution. What if the discrepancy isn't in the clocks but in our position in the cosmic room? Their hypothesis was that we reside inside an enormous underdensity of matter, a local supervoid now known as the KBC void. This wouldn't be a typical void like Boötes. This would be a void on a truly grand scale, a spherical region of space spanning approximately 2 billion light-years in diameter, with our Milky Way sitting right at its center. In this model, the local universe around us is significantly emptier than the cosmic average. The physics of how this void could explain the Hubble tension is subtle yet profound. It revolves around two key concepts: gravitational potential and the peculiar velocity it induces. First, imagine our local underdensity. Because there is less matter inside this vast region, the gravitational pull holding us here is weaker than it should be. Meanwhile, the surrounding regions of the universe, which have the average density, exert a much stronger gravitational pull. This imbalance creates a net effect. We are being pulled outward, away from the center of the void and toward the denser walls surrounding it. Our entire local group of galaxies is therefore moving with an additional, peculiar velocity on top of the general expansion of the universe. Second, the underdensity itself affects the path of light. As photons from distant supernova travel through the void, they traverse a region with weaker gravity. Climbing out of this shallower gravitational well takes less energy than if the universe were uniformly dense, causing the light to be less redshifted than we would otherwise expect. When we combine these two effects, our own motion outward and the altered redshift of the light we see, it could create the illusion that nearby galaxies are receding from us faster than they truly are, perfectly accounting for the higher local measurement of the Hubble constant. The evidence for this void is compelling yet indirect, built upon a growing body of large-scale galaxy surveys. These three-dimensional maps of our cosmic neighborhood, such as those from the 2MASS and SDSS projects, do seem to show that we are surrounded by a hierarchy of voids. Our local group exists in a small void, which is part of the local void, which itself appears to be nestled within an even larger underdensity. Proponents of the KBC model argue that these nested voids collectively form a single, massive supervoid. They point to statistical analyses showing that the density of galaxies increases with distance from us, up to a scale of about 1 billion light-years, which would be consistent with residing near the center of such an immense structure. However, the KBC void remains deeply controversial, and many cosmologists are not yet convinced. The primary criticism is one of probability and statistics. The standard model of cosmology, which includes dark energy and cold dark matter, does allow for voids to form, but a void this large with our galaxy perfectly at its center would be exceptionally rare. It would be a staggering cosmic coincidence, like finding a single perfectly round grain of sand on an entire beach and then discovering you're standing right in the middle of it. Critics argue that while smaller voids are common, a 2 billion light-year underdensity stretches the predictions of the standard model to its breaking point. Furthermore, some independent analyses of galaxy surveys have failed to find conclusive evidence for a void of the precise size and emptiness required to fully resolve the Hubble tension. The signal, they argue, is too weak and could be influenced by other large-scale structures or observational biases. The implications of this debate extend far beyond a simple mapping exercise. If the KBC void is confirmed, it would be a monumental discovery that effectively solves the Hubble tension without requiring any new physics. It would mean our standard cosmological model is correct, and the discrepancy was simply caused by our unfortunate or fortunate position in a giant cosmic bubble. We could breathe a sigh of relief that the foundations of physics remain intact. However, if further, more precise observations rule out the void's existence, the Hubble tension becomes an even more urgent crisis. It would force us to accept that our understanding of the universe is fundamentally incomplete, potentially requiring new types of dark energy, modifications to Einstein's theory of gravity, or other exotic physics beyond our current models. The search for the KBC void is ultimately a search for objectivity. It forces us to ask if we can ever take a truly unbiased measurement of the universe, or if our local environment forever colors our perspective. Whether it is ultimately proven to be real or dismissed as a statistical fluke, this proposed structure highlights a profound truth about cosmology. To understand the grandest scales of the cosmos, we must first fully understand our own unique place within it. The void is a mirror reflecting both the contents of the universe and the limitations of our own viewpoint. This mysterious motion, known to astronomers as dark flow, presents us with one of the most profound and unsettling puzzles in all of modern cosmology. Picture the universe's expansion not as a serene, uniform stretching, but as a vast, rolling river. Most galaxies are like leaves on that river, carried along smoothly by the current. But now, imagine spotting a large group of leaves all moving together in the same direction, against the flow or sideways, as if pulled by some unseen underwater current. That is the essence of dark flow, the perplexing observation that entire clusters of galaxies, enormous structures containing thousands of galaxies each, are drifting in a coordinated motion at astonishing speeds of up to 1,000 kilometers per second, all toward a particular patch of space beyond the observable horizon. The evidence for this phenomenon was painstakingly gathered by analyzing the cosmic microwave background, the same ancient afterglow that revealed the cold spot. Researchers meticulously studied the light from distant galaxy clusters, looking for a subtle distortion known as the kinematical Sunyaev-Zeldovich effect. This complex name describes a brilliant technique. As the faint microwave background radiation passes through the superheated gas that permeates a galaxy cluster, the motion of that cluster imprints a tiny shift on the radiation's temperature. It acts like a cosmic speed camera, allowing scientists to measure the cluster's peculiar velocity, its individual motion over and above the general expansion of the universe. When they compiled these measurements for over 1,000 clusters, a startling pattern emerged. These colossal objects weren't moving randomly. They showed a persistent, coherent stream toward a single direction in the sky, a flow that continued for billions of light years, far beyond the scale where such coordinated movement should be possible according to standard cosmology. This is where the mystery deepens into truly uncharted territory. Within the framework of the standard model, the gravitational forces that could cause such a bulk motion must come from matter within our observable universe. The gravitational pull of known superclusters like the Shapley Attractor does influence our local region, but its reach is limited. The dark flow signal, however, persists across distances so vast that the material causing it should be well within our viewable cosmos. But it isn't. There is no sufficiently massive concentration of matter in that direction to account for this relentless pull. This leads to a staggering, almost heretical possibility. The gravitational source for dark flow must lie beyond the boundary of our observable universe. The implications of this are enough to redefine our entire conception of reality. If confirmed, dark flow suggests that the structure of the cosmos extends far beyond the 93 billion light-year sphere of space we can see. The observable universe, the portion from which light has had time to reach us since the Big Bang, may be just one small part of a much larger, perhaps infinite, whole. The gravitational tug felt by all those galaxy clusters could be coming from a supercluster of unimaginable proportions residing in this unobservable realm, a structure so immense that its gravity ripples across the existential divide to orchestrate the motion of everything in our local neighborhood. This isn't just a new object, it's a window into the infinite, a hint that our universe is part of a grander architecture we are only beginning to sense. Naturally, a claim this extraordinary faces intense scrutiny and demands extraordinary evidence. The scientific community has responded with healthy skepticism, probing the methodology for potential systematic errors. Could this signal be an artifact of how we measure the cosmic microwave background? Might there be an unknown source of contamination in the data from our own galaxy? Some subsequent studies have failed to detect the effect with the same confidence, while others have found supporting evidence, keeping the debate very much alive. The challenge is immense, as measuring these tiny imprints on the most ancient light in the universe pushes our technology and our statistics to their absolute limits. Whether dark flow is ultimately validated or dismissed as a measurement anomaly, its investigation has already profoundly impacted cosmology. It forces us to confront the limits of our knowledge and the possibility that the true nature of reality lies beyond our current horizon. It challenges the cosmological principle in a new way, not by showing an irregularity in the distribution of matter, but by revealing a potential irregularity in the very motion of the cosmos on the largest scales. This mysterious flow is a siren's call, pulling our curiosity toward the ultimate horizon and compelling us to ask what unimaginable structures might lie in the darkness beyond the light we can see. But this grand, coordinated drift we call dark flow is not the only mysterious motion hidden in the cosmos. Some of the most intriguing shifts in structure are not happening on the scale of galaxy clusters, but within the very fabric of individual galaxies themselves. We now turn our gaze from the immense and hypothetical to the closer and observable, to a phenomenon that has twisted the shapes of galaxies right in our own neighborhood. This brings us to the curious case of galactic warps, where the pristine disks of spiral galaxies are bent into elegant cosmic smiles. Picture a spiral galaxy in your mind. You likely imagine a perfectly flat, thin disk of stars and gas spinning gracefully like a frisbee thrown through the void. For a long time, astronomers believed this was the standard state. But the universe adores complexity. We now know that a vast majority of spiral galaxies, including our own Milky Way and our great neighbor Andromeda, are not flat at all. Their outer disks are bent upwards or downwards, creating a distinctive warp that often makes the galaxy look like a fedora hat or a curved potato chip. This isn't a rare defect, it's a common feature of galactic anatomy, a subtle distortion that holds clues to a galaxy's history and its invisible surroundings. Our own Milky Way provides a perfect and intimate example. For centuries, we were oblivious to our galaxy's warp because we are embedded within it. It was only through meticulous radio astronomy, mapping the distribution of cold hydrogen gas that extends far beyond the visible star disk, that we could finally step back and see the true shape of our home. What these maps revealed was stunning. The Milky Way's disk of gas is not flat. It is twisted into a complex integral sine shape, a graceful S-curve where one side of the galaxy bends upward and the opposite side bends downward. This warp begins about 60,000 light-years from the center and becomes more pronounced in the outermost reaches, affecting the vast, sparse reservoir of gas that is the future fuel for star formation. The pressing question is, what force is strong enough to bend an entire galaxy? A single galaxy's disk contains hundreds of billions of stars, all bound by immense gravitational forces. Warping such a colossal structure requires a sustained and powerful external influence. For decades, the prime suspect has been the mysterious dark matter halo that envelops our galaxy. The classic view is that this halo is a smooth, spherical cloud. But what if it isn't? One compelling theory suggests that the dark matter halo itself could be slightly flattened or tilted relative to the visible disk. If the halo's gravitational field is not perfectly symmetrical, it can exert a torque on the outer disk, gradually pulling it into a warped configuration over billions of years. The warp, in this case, is a visible sign of the invisible dark matter skeleton's true, asymmetric shape. However, dark matter isn't the only suspect in the investigation. Another powerful force could be at work, a recent gravitational encounter. Our Milky Way is not isolated. It is surrounded by an entourage of satellite galaxies, most notably the large and small Magellanic Cloud. These galaxies are currently swinging close to us on their orbital path, and they are not mere specks of light. They are massive, and they are dragging along an enormous envelope of dark matter and gas, the Magellanic system we discussed earlier. As this system plows through the dark matter halo surrounding the Milky Way, it creates a wake, a gravitational disturbance. Think of a speedboat moving through water. It creates a bow wave and a wake that trails behind it. In the same way, the motion of the Magellanic Clouds could be dynamically disturbing the dark matter, creating a gravitational wake that pulls on our galaxy's disk and induces the pronounced warp we observe. Recent sophisticated simulations have shown this to be a remarkably effective mechanism, potentially explaining the timing and specific shape of our galaxy's bend. Yet there is a third, more elusive force that might contribute to the puzzle: intergalactic magnetic fields. Space is not a perfect vacuum. It is threaded with vast, diffuse magnetic fields that exist in the spaces between galaxies. While incredibly weak compared to a common fridge magnet, these fields operate on a truly galactic scale. If a galaxy is moving through such a magnetized medium, the interaction between the galaxy's own ionized gas and the external field could, in theory, exert enough pressure to contribute to a warp. It would be a slow, gentle bending, like a sheet of paper being curved by a steady breeze. While this mechanism is unlikely to be the sole cause, it could be a contributing factor, working in concert with gravitational effects to sculpt the final, warped shape of the galactic disk. The story becomes even richer when we look at our closest galactic relative, the Andromeda Galaxy. With its magnificent, tilted spiral arms, Andromeda also possesses a significant warp in its outer disk. This presents a fascinating comparative study. The Milky Way's warp is often linked to the influence of its satellite galaxies, but Andromeda's satellite system is different, dominated by a recent major collision that created its giant stellar halo. This suggests that while the symptoms, the warps, are similar, the underlying causes in each galaxy might be unique. For Andromeda, its warp could be the lasting ripple from a past merger, a gravitational echo of a smaller galaxy that was torn apart and consumed billions of years ago. Studying these two warps side by side allows astronomers to compare and contrast, to see how different galactic environments and histories produce the same general phenomenon through potentially different physical pathways. Ultimately, the galactic warp is more than a curiosity. It is a dynamic fingerprint. Its specific shape, its amplitude, and even the way it moves around the galaxy, a phenomenon known as warp precession, encode a record of the forces that have acted upon the galaxy over the last few billion years. By carefully measuring and modeling warps, we are not just mapping the visible stars, we are indirectly charting the distribution of invisible dark matter, tracing the orbits of satellite galaxies, and perhaps even sensing the faint pull of intergalactic magnetic fields. A warp is a sign that a galaxy is a living, evolving entity, constantly being shaped and reshaped by its interactions with the dark and visible cosmos alike. It is a subtle bend in the fabric of a billion stars, telling a story of unseen masses and ancient encounters. Yet this grand emptiness we call the Eridanus supervoid is not merely a passive absence. It is a dynamic actor in the cosmic play, and its primary role was to serve as a potential explanation for one of the most perplexing mysteries in modern cosmology. The story begins not with the void itself, but with a cold spot, a chilling anomaly frozen in the oldest light we can see. When the Wilkinson microwave anisotropy probe first mapped the cosmic microwave background in exquisite detail, it revealed the universe's infant portrait, a remarkably uniform canvas of subtle hot and cold variations, the quantum seeds of all future structure. But one region stood out as profoundly different. The CMB Cold Spot was not a minor fluctuation. It was a significant and statistically startling dip in temperature, a cold patch so large and so pronounced that it seemed to defy the standard model of cosmic evolution. It was a cosmic bruise that demanded an explanation. The most elegant and straightforward theory proposed that the cold spot was not a primordial feature at all, but a secondary effect, an illusion created by the vast emptiness of the Eridanus supervoid. This explanation hinges on a fascinating consequence of general relativity and the universe's expansion known as the integrated Sachs-Wolf effect. Here's how it works. As photons from the CMB travel across the cosmos for billions of years to reach us, they must navigate the evolving gravitational landscape. When a photon enters a gravitational well, like a dense cluster of galaxies, it gains energy, appearing slightly hotter or blue-shifted. But as it climbs out, it loses that energy, becoming slightly cooler or redshifted. In a universe with no dark energy, these effects would perfectly cancel out. However, our universe is dominated by dark energy, which causes the expansion to accelerate. This acceleration weakens gravitational potentials over time, so by the time a CMB photon finishes climbing out of a vast, ancient structure, the well has become shallower. The photon loses more energy escaping than it gained entering, resulting in a net energy loss. For a photon passing through a supervoid, an immense underdensity, the reverse is true. It enters a hill of weak gravity and exits into a region of average density, but because the void itself is expanding and becoming even emptier due to dark energy, the photon actually gains a tiny amount of energy, making it appear slightly hotter. Wait, that would create a hot spot, not a cold one. The confusion here is common. The key is the photon's entire journey. The most significant ISW effect for a void actually creates a cold spot because the photon, upon leaving the diminishing gravitational potential of the expanding void, is left with less energy than it would have had if the void's gravity had remained static. It's a subtle, counterintuitive process, but the bottom line was that a supervoid of the right size and depth could, in theory, cast a cold shadow on the CMB, perfectly explaining the mysterious cold spot. The discovery of the Eridanus supervoid, an underdense region hundreds of millions of light-years across, sitting right along the line of sight to the cold spot, seemed like a perfect case closed. It was the ideal culprit, a cosmic sinkhole whose gravitational influence could imprint the observed chill on the ancient light. But as astronomers measured the void more carefully, the elegant solution began to unravel. The problem was a matter of potency. The Eridanus supervoid is certainly large, but it is not nearly empty enough to account for the profound temperature drop seen in the cold spot. The math simply doesn't add up. The void's gravitational influence is too weak by a factor of about 10 to produce such a dramatic effect. It would be like a small pothole causing a car to bounce as if it had driven off a cliff. The void might be contributing a small part of the signal, but it cannot be the sole architect of the anomaly. This left cosmologists with a troubling void and a cold spot that remained, for the most part, unexplained. This failure to fully explain the cold spot forces us to confront the deeper mysteries of void formation itself. Why is the Eridanus supervoid, and many others like it, so much emptier than our best cosmological simulations predict? In the Standard Model, voids are born from the tiniest underdensities in the early universe. As the cosmos expands, these regions expand faster than their surroundings, becoming ever more empty as matter flows out toward the denser filament walls. Our supercomputer simulations, which brilliantly replicate the cosmic web of clusters and filaments, consistently produce voids that are too busy. They are filled with a faint, foamy network of small dark matter halos that should host a sprinkling of faint dwarf galaxies. But when we look at real voids like Eridanus, we find them are far more pristine and empty than the simulations allow. This is known as the void phenomenon problem. The leading theory to solve this puzzle points to feedback from another of the universe's great forces, supernova. In the early universe, even the slightest overdensities would have collapsed to form the first generation of stars. These first stars were behemoths, living short, violent lives and exploding as supernovae of tremendous power. In the dense environments of future galaxy clusters, this explosive energy was contained by the deep gravitational wells. But in the proto-void regions, where the gravitational pull was already weak, these early supernovae could have had a catastrophic and cleansing effect. Their powerful winds could have blown out nearly all of the leftover gas, preventing the formation of those myriad small dwarf galaxies that the simulations predict. The voids were not born completely empty. They were scoured clean by the first fireworks of star formation. This would leave the vast regions we see today not as absolute vacuums, but as incredibly sparse deserts, largely devoid of the faint galactic fauna that our models insist should be there. The Eridanus supervoid, therefore, is not just an empty space. It is a fossil relic from the era of the first stars, a region sterilized by the very explosions that also seeded the universe with the heavy elements necessary for life. Its profound emptiness is a lasting echo of the first and most powerful storms that ever swept through the cosmos. For all our powerful telescopes and ambitious surveys, there remains a fundamental blind spot in our cosmic vision, a place where the very heart of our own galaxy blocks our view of the universe beyond. This is the Zone of Avoidance, a sprawling region of the sky that accounts for about 20% of the entire celestial sphere, where the dense band of the Milky Way creates a near-impenetrable wall of stars, gas, and dust. Imagine trying to map a landscape while standing in the middle of a dazzling, glittering forest. The very trees that surround you prevent you from seeing what lies on the other side of the wood. For centuries, this zone lived up to its name, effectively avoiding any detailed observation and forcing astronomers to map the cosmos with a giant Milky Way-shaped hole in their data. It wasn't just an empty area on a chart. It was a cloak of invisibility, potentially draping entire galaxies, clusters, and even larger structures from our view. The primary obstacles are twofold: sheer starlight and thick cosmic dust. The first is a problem of glare. Within the plane of the Milky Way, the concentration of stars is so immense that their combined light washes out the far fainter glow of distant background galaxies. It's like trying to spot a single, distant candle flame while staring directly into the beam of a searchlight. The second, more pernicious problem is interstellar extinction. The spiral arms of our galaxy are filled with microscopic grains of silicon and carbon, essentially fine, opaque smoke. This dust doesn't just block visible light, it absorbs and scatters it, dimming and reddening the light from any object that lies behind it. For traditional optical telescopes, this combination of glare and grime made the zone of avoidance a professional dead end, a place where cosmology simply stopped. But where visible light fails, other forms of radiation can triumph. The great leap forward came with the advent of astronomy in non-visible wavelengths, particularly infrared and radio. Cosmic dust, which is so effective at blocking visible light, actually glows with heat in the infrared. While it hides the optical universe, it reveals its own structure in stunning detail, allowing us to map the obscuring filaments themselves. More importantly, infrared light has a longer wavelength than visible light, allowing it to punch through the dust clouds with far less scattering. A background galaxy that is completely invisible to an optical telescope can often be detected by its infrared heat signature. Radio waves, with their even longer wavelengths, are the ultimate penetrators, flowing through the dust as if it weren't even there. By switching from eyes that see light to ears that hear radio, astronomers finally found a way to listen to the secrets hidden behind the galactic curtain. This multi-wavelength assault has already yielded shocking discoveries, completely rewriting the map of our local universe. One of the most dramatic finds was the entire Vela Supercluster, a massive wall of galaxies lying almost directly behind the Milky Way's disk, unveiled through painstaking surveys that pieced together thousands of faint galaxy redshifts. Perhaps the most famous discovery was that of the galaxy Dwinjaloo 1. In 1994, astronomers using a radio telescope in the Netherlands were mapping hydrogen gas emissions and stumbled upon a spiral galaxy a mere 10 million light-years away, a major galactic neighbor that had been completely hidden from view our entire history. It was a stark reminder that we had been missing fundamental pieces of our cosmic local group, simply because they were parked in our blind spot. The greatest prize, however, and the subject of intense ongoing research, is the potential discovery of the unknown gravitational source contributing to the Great Attractor. This mysterious region, pulling our entire local group and thousands of other galaxies toward it, lies deep within the Zone of Avoidance. While we've identified some massive clusters like the Norma cluster as part of this complex, the full extent of the mass responsible for this immense pull remains hidden. Is there a previously undetected supercluster of staggering proportions lying in wait? Current evidence suggests the mass we can account for is still not enough to explain the observed motion, meaning there could be an even larger concentration of galaxies and dark matter still obscured, waiting to be discovered. Every new galaxy found in the zone helps to balance the gravitational ledgers and brings us closer to solving this decades-old mystery. The effort to lift this cosmic veil is a global endeavor, spearheaded by dedicated surveys like the VLA Zone of Avoidance Survey and the wise use of space-based observatories like the Spitzer and James Webb Space Telescopes, whose infrared eyes are unparalleled. Each new dataset is like a flashlight beam piercing the darkness, slowly illuminating the outlines of what was once a terra incognita on the cosmic map. What they reveal will do more than just fill in a blank spot. It will complete our census of the local universe, finally allowing us to see the full gravitational field that governs our motion and to understand our true place in the cosmic web. The Zone of Avoidance is a reminder that sometimes the biggest secrets are hidden not in the farthest reaches of space, but in the most obvious place, right in front of us, obscured by the brilliant light of our own galactic home. Yet this epic dance of galaxies, from the colossal flows of dark flow to the subtle warping of disks, is not just a story of motion and interaction, it is often a story of consumption. The universe operates on a principle of cosmic survival of the fittest, where larger galaxies grow by devouring their smaller neighbors. But these ancient acts of galactic cannibalism are not clean. They leave behind forensic evidence, ghostly remnants that swirl around the victorious galaxy like cosmic DNA, telling the story of its violent past. Our own Milky Way, a seemingly serene spiral, is in fact a celestial predator, and the fossilized remains of its meals are still visible, etched across our sky in streams of stars. The most stunning and obvious of these remnants is the Sagittarius dwarf spheroidal galaxy and the magnificent stream of stars it has left in its wake. Discovered in 1994, this small companion galaxy was caught in the act of being devoured. It's a tragic and beautiful sight. The main body of the dwarf galaxy is now a tattered wreck, having made numerous passes through the plane of our galaxy. With each passage, the Milky Way's immense gravity has pulled it apart, stripping away its stars and scattering them into two vast, ribbon-like structures that loop entirely around the sky. These are the Sagittarius streams, one leading the dwarf's motion and one trailing behind it. From our perspective inside the Milky Way, these streams are seen as a colossal river of stars, arching over the night sky from one horizon to the other. It is the most prominent stellar stream known, a testament to a slow-motion destruction that has been unfolding for billions of years. Studying this stream is like reading a history book written in starlight. The specific paths of the stars within it encode precise information about the gravitational field of the Milky Way's dark matter halo. Because these stars are being tugged only by gravity, they trace out the underlying shape and density of the invisible matter that dominates our galaxy's mass. Their orbits have revealed that our halo is not a perfect sphere, but is slightly flattened like a squashed beach ball. Furthermore, the stream shows signs of intricate wrinkling and clumping. These aren't random, they are thought to be the gravitational wake caused by dark matter subhalos, small, invisible clumps of dark matter that litter the galactic halo. The Sagittarius stream is therefore far more than a tidal tale. It is the most sensitive probe we have for mapping the distribution and clumpiness of the dark matter that shapes our entire galaxy. But the Sagittarius dwarf is merely the most recent meal. To find evidence of a far more ancient and catastrophic collision, we must turn to the data from the European Space Agency's Gaia mission. This ambitious project is meticulously mapping the positions, distances, and motions of over 1 billion stars in our galaxy, creating an unprecedented three-dimensional movie of the Milky Way. Within this vast trove of data, astronomers discovered something bizarre. A large population of stars near the galactic center that were moving in a radically different way from the rest. Instead of orbiting serenely in the galactic disk, these stars were on extremely radial orbits, plunging headlong toward the galactic center like comets falling toward the sun, then swinging out to great distances before falling back again. When the velocities of these stars were plotted, they formed a distinctive shape in the data, a thick, sausage-like blob. This structure was promptly nicknamed the Gaia sausage, or more formally, the Gaia Enceladus sausage. This was not a stream, it was the ghost of an entire galaxy. The evidence suggests that between 8 and 11 billion years ago, a sizable dwarf galaxy, perhaps 1/4 the mass of the Milky Way at the time, plunged head-on into our nascent galaxy. This was not a glancing blow like the Sagittarius interaction. This was a direct, catastrophic merger. The collision would have been devastating, violently shaking the Milky Way and likely shredding its disk, which at the time was still forming. The stars from the victim galaxy were scattered throughout the inner halo of the Milky Way, their chaotic, radial orbits a permanent record of the impact. This single event is now believed to have fundamentally reshaped our galaxy, contributing a significant fraction of the stars in our galactic halo, and perhaps even triggering the formation of the Milky Way's thick disk. These fossil structures are transforming our understanding of galaxy growth. We once imagined galaxies forming in serene isolation, gently accumulating gas to form stars. The reality is a history written in violence. The halo of our galaxy is not a smooth, pristine cloud of old stars. It is a galactic graveyard, an archaeological dig site built from the remnants of countless smaller galaxies that were consumed over billions of years. Each stream and stellar population is a layer of history. By dissecting the chemical compositions of these stars, astronomers can perform cosmic archaeology. Stars born in different galaxies have unique chemical signatures based on the specific history of star formation and supernova enrichment within their original homes. Stars from the Gaia Sausage, for instance, have a different metallicity, a different abundance of heavy elements than the oldest stars native to the Milky Way, confirming their foreign origin. The discovery of these remnants forces us to see our home galaxy not as a static island universe, but as a dynamic, evolving entity with a rich and violent biography. It is a product of a hierarchical universe built from the bottom up through a series of mergers and acquisitions. Every time we look up at the night sky, we are surrounded by the ghosts of galaxies that no longer exist, their stars now forever part of our own. Their silent testimony tells a story of chaos and destruction, but also of creation and growth, revealing that the majestic spiral we call home was forged in the fires of ancient collisions. But perhaps the most compelling chapter in this gravitational mystery is the role of a titan we've already met, the Norma Cluster. Lying about 200 million light-years away, this massive cluster of galaxies, also known as Abell 3627, sits right in the predicted path of the Great Attractor. For a long time, it was considered the prime candidate, the obvious source of all that pull. It is indeed a colossal concentration of mass, containing hundreds of galaxies and vast clouds of searing hot X-ray emitting gas, all bound by a tremendous amount of dark matter. Its gravity is undeniable, and it certainly contributes to the motion of our local group. But as astronomers made more precise measurements, a sobering reality set in. The Norma Cluster, as immense as it is still not enough. Even when combined with the mass of the entire Centaurus Wall complex, the gravitational tally still comes up short. The math indicates there must be something even larger behind it, a deeper, more massive concentration of matter that we have yet to fully unveil. The Norma Cluster is not the Great Attractor itself. It is more like the most prominent landmark on the shore of a much deeper ocean, a signpost pointing toward an even greater hidden depth. This is where the mystery truly deepens, because the suspected core of the Great Attractor lies almost perfectly behind the densest part of our own galaxy's disk, a region astronomers call the Zone of Avoidance. This is a place where the Milky Way's swirling arms of stars, gas, and thick cosmic dust become an almost impenetrable curtain, blocking our view of the distant universe beyond. It's our galaxy's ultimate blind spot, a brilliant and frustrating obstacle that has kept the heart of the Great Attractor hidden from optical telescopes for decades. Trying to see through it is like trying to peer through a dense, glittering fog. The very stuff of our home obscures the very thing we are trying to find. Undeterred, astronomers have turned to technology that can see what our eyes cannot. They have launched a multi-wavelength assault on the Zone of Avoidance, using telescopes that see the universe in radio waves and infrared light. These longer wavelengths can punch through the cosmic dust that blocks visible light, revealing the secrets hidden behind the veil. Radio surveys meticulously map the distribution of neutral hydrogen gas in distant galaxies, while infrared telescopes like the Spitzer Space Telescope and the James Webb Space Telescope detect the heat signatures of stars and galaxies, seeing them not by their visible light but by their warmth. These efforts have been remarkably successful, peeling back the galactic curtain to reveal a startlingly crowded universe behind the Milky Way. They have uncovered entire new galaxies and confirmed that the Centaurus Wall and the Norma Cluster are indeed just the beginning of a much larger structure, now often referred to as the Vela Supercluster or the broader Laniakea Supercluster, which encompasses our own galactic neighborhood and flows toward the Great Attractor. So what is the leading theory today? The current best explanation is that the Great Attractor is not a single, incomprehensibly dense object, but rather the collective gravitational pull of this entire massive supercluster complex. It is the combined weight of the Norma Cluster, the Centaurus Wall, the Vela Supercluster, and likely other enormous concentrations of mass that we are still mapping in that direction. It is the gravitational core of our local volume of the universe, the deepest well in our part of the cosmic web. Our Milky Way, along with thousands of other galaxies, is simply flowing down this slope of space-time toward the densest node in our celestial neighborhood. The mystery is transforming from a search for a single monster in the dark to the process of completing a three-dimensional map of an entire continent of galaxies, much of which has been hidden from our view until very recently. The pursuit of the Great Attractor has fundamentally changed our understanding of our place in the cosmos, revealing that we are part of a vast, flowing river of galaxies, all moving together toward a common destination in the immense heavens. But if the violent history of galactic mergers reveals a universe built on consumption, our next destination presents a cosmos of profound silence and absence. We now turn from the bright streams of devoured stars to the shadowy, almost invisible realms of dark galaxies, theoretical islands in the cosmos where dark matter reigns supreme, and the brilliant fireworks of starlight have all but fizzled out. Imagine an object with the mass and gravity of a giant galaxy like our Milky Way, but when you point your most powerful telescope at it, you see almost nothing. Just a faint, ghostly smudge where there should be a whirlpool of billions of stars. This isn't a void, it's a galaxy that forgot to form stars, a cosmic paradox that challenges the very foundation of how we think galaxies are born. The story of these enigmatic objects begins with a class of galaxies so faint and diffuse they were almost missed entirely. For decades, astronomers believed large galaxies had to be bright with a high density of stars. That changed with the discovery of ultra-diffuse galaxies. These are enormous, galaxy-sized objects, but their stars are spread so thin that they emit very little light, making them incredibly difficult to detect. They are the cosmic equivalent of a vast, thin cloud, huge in size but almost transparent. While studying the Coma cluster, a dense gathering of thousands of galaxies, astronomers found dozens of these faint ghosts. Most were intriguing, but one stood out as profoundly strange: Dragonfly 44. On the surface, Dragonfly 44 is utterly unimpressive. It is a faint, fuzzy patch of light containing very few stars, about 100 times fewer than the Milky Way. If it were only made of what we can see, it would be an unremarkable dwarf galaxy. But when astronomers measured the velocities of its stars and its globular clusters, they got a shock. Those visible objects were moving at incredibly high speeds, speeds that only make sense if they are being whipped around by the gravitational pull of a tremendous amount of invisible mass. The math revealed that Dragonfly 44 has a mass comparable to our Milky Way, a giant galaxy, but 99.99% of that mass is completely dark. It is a galaxy-sized halo of dark matter with barely any stars to illuminate it. Finding Dragonfly 44 was like finding the invisible skeleton of a giant beast, with only a few fireflies trapped inside to hint at its immense outline. The existence of such an object turns galaxy formation theory on its head. The standard model is a partnership between dark matter and normal matter. First, a halo of dark matter collapses, providing the gravitational seed. Then ordinary gas falls into this halo, cools, condenses, and eventually forms stars. The ratio of dark matter to normal matter is generally expected to be within a certain range. A dark galaxy like Dragonfly 44 completely shatters this expectation. It poses a fundamental question: why did this massive dark matter halo fail to collect and convert its gas into stars? Several theories attempt to explain this failure. Perhaps the galaxy formed in a particularly empty region of space where there was very little gas to accrete in the first place, leaving its dark matter halo starved of star-forming fuel. Alternatively, the galaxy might have formed stars early on, but some violent event like a relentless barrage of supernova explosions or the intense energy from a central black hole could have blown all the remaining gas out, permanently shutting down any future star formation and leaving behind a dark, sterile husk. Yet Dragonfly 44 is not alone. Other candidates, like the even more extreme Antlia 2, a dwarf galaxy orbiting the Milky Way that is far too diffuse for its mass, suggest that dark galaxies might be a more common part of the cosmic ecosystem than we ever imagined. This opens up a fascinating possibility. Could these dark galaxies be the missing links in our understanding of dark matter itself? They are, in effect, almost perfect laboratories for studying dark matter in isolation, free from the complicating bright lights and magnetic fields of abundant normal matter. If we can find enough of them and measure their properties, we could finally get crucial clues about how dark matter particles interact with each other. Do they simply pass through one another, or can they collide and scatter? The internal structure of a pure dark matter halo could hold the answer. The hunt for these cosmic ghosts is now a major frontier in astronomy. It requires innovative techniques like looking for the subtle gravitational lensing effects they impose on the light of more distant galaxies, or searching for the faint radio signals that might be emitted by the tiny amount of gas swirling within them. Each new candidate discovered forces us to reconsider the intricate dance between dark and light matter, suggesting that the recipe for building a galaxy has far more failed outcomes and strange variations than we ever thought. These dark galaxies are the silent, invisible giants of the cosmos, reminding us that what we see with our eyes is only the smallest fraction of the universe's true story, and that the greatest structures are often those hidden in plain sight. But before the Sloan Great Wall or the Hercules-Corona Borealis Great Wall captivated astronomers, there was a discovery that first ripped open the textbook and rewrote our understanding of the cosmos on the largest scales. This is the story of the CFA2 Great Wall, a structure that, at the time of its revelation, was so immense it seemed to strain the very laws of physics. Its discovery in 1989 was a watershed moment, the first time we looked into the deep universe and saw not random scatter, but architecture. The project that made it possible was the Center for Astrophysics Redshift Survey, or CFA2, a monumental effort to map the three-dimensional positions of galaxies in our local universe. For the first time, astronomers weren't just looking at points of light on a flat plane. They were calculating their distances, building a true depth map of the cosmos. What emerged from this data was nothing short of breathtaking. The galaxies were not distributed evenly. Instead, they were arranged in a colossal, flat sheet, a wall, that stretched for an astonishing 500 million light-years. To grasp that scale, imagine a structure so long that a beam of light, the fastest thing in the universe, would take 500 million years to travel from one end to the other. Our entire local group of galaxies would be nothing more than a single, tiny brick in this vast cosmic edifice. The existence of such a structure delivered a profound shock to the field of cosmology. The prevailing belief, rooted in the cosmological principle, was that on large enough scales, the universe was smooth and homogeneous. The CFA2 wall was a direct and stunning contradiction. It was a glaring irregularity, a concentration of matter so huge it forced scientists to radically reconsider their models of how the universe evolved after the Big Bang. It proved that gravity had been far more effective at clumping matter together than anyone had previously dared to imagine, and it hinted that the initial seeds of the universe's structure were far lumpier than theory predicted. This discovery did more than just break records. It fundamentally changed the way astronomers saw the sky. It was the first conclusive evidence for the cosmic web, the idea that galaxies are arranged in a vast, interconnected network of filamentary walls separated by immense voids. The CFA2 wall was our first clear glimpse of one of these thick, dense threads. It taught us to stop thinking of galaxies as isolated islands and to start seeing them as nodes in a grand, universal tapestry, woven together by the invisible hand of gravity and dark matter. Perhaps its greatest legacy, however, was the path it paved. The CFA2 wall proved that such enormous structures were not only possible but detectable. It gave astronomers the courage to launch ever larger and more ambitious sky surveys, confident that they would find even greater wonders hidden in the data. This confidence directly led to the Sloan Digital Sky Survey and the subsequent discoveries of the Sloan Great Wall and the Hercules-Corona Borealis Great Wall. Each new discovery built upon the foundation laid by the CFA2 survey, each new wall pushing the boundaries of size and complexity further than we thought possible. It was the pioneer, the first giant that showed us the cosmos was capable of building on a scale that dwarfed our wildest imaginations, setting the stage for a new era of cosmic cartography that continues to reveal the universe's grand design. Yet for all the immense power of gravity and the explosive fury of stars, there is a far more subtle and pervasive force weaving its way through the cosmic web, a silent architect that shapes the lives of galaxies from within. We now turn our attention from the grand dance of dark matter to the delicate, invisible threads that are spun between the stars themselves, the enigmatic galactic magnetic fields. Imagine a force so diffuse that its total strength is 1,000,000 times weaker than the Earth's own magnetic field. A pull so gentle you would never feel it. Now imagine that same force organized on a scale so vast that it can span an entire galaxy, weaving through interstellar space for hundreds of thousands of light years. This is the reality of galactic magnetism. These fields are not concentrated into obvious north and south poles. Instead, they are a complex, tangled web of magnetic lines of force that permeate the thin gas between the stars, acting as a cosmic guidance system for the most energetic particles in the universe. The origin of these immense magnetic structures is one of the great unsolved puzzles in astrophysics. The most promising theory is known as the dynamo effect. Imagine a simple, weak magnetic seed field, perhaps a relic from the earliest moments of the universe. As a galaxy rotates, its swirling disk of ionized gas, a plasma made of charged particles, acts like a gigantic electrical generator. This moving, conducting fluid stretches, twists, and folds the weak magnetic field lines, amplifying them and organizing them into the large-scale patterns we observe today. It's a self-sustaining process. The motion of the gas strengthens the magnetic field, and the magnetic field, in turn, influences the motion of the gas. This galactic dynamo is thought to be the engine that builds and maintains these fields over billions of years, transforming a faint whisper of magnetism into a galaxy-spanning force. Despite their incredible weakness, these magnetic fields play a surprisingly powerful role in the life of a galaxy. Their most visible influence is on the very stuff of creation, cosmic dust. Within giant molecular clouds, the cold, dense nurseries where stars are born, magnetic fields provide a supporting skeleton against the relentless crush of gravity. As a cloud collapses to form new stars, the magnetic pressure helps regulate the process, slowing the collapse and potentially determining the final size and number of stars that are born. They are the invisible scaffolding that guides the architecture of star formation. Furthermore, these fields align the tiny, needle-like dust grains that fill interstellar space, causing them to spin and orient themselves perpendicular to the magnetic field lines. This alignment is what creates the beautiful phenomenon of starlight polarization, where light from distant stars appears subtly filtered, offering astronomers a way to indirectly map the invisible magnetic field structures they could never see directly. Perhaps their most dramatic role, however, is as a galactic highway system for cosmic rays. These are not rays of light, but atomic nuclei, mostly protons, that have been accelerated to nearly the speed of light by supernova explosions or active black holes. These particles are so energetic that, if left unchecked, they would zip straight out of the galaxy in an instant, but they are charged, and that makes them susceptible to magnetism. The galaxy's magnetic field acts as a vast, chaotic maze of winding paths. A cosmic ray doesn't travel in a straight line. It spirals tightly around a magnetic field line, bouncing and scattering from one region to another. This process effectively traps the particles within the galactic disk, confining them for millions of years and forcing them to travel a convoluted path far longer than the straight line distance. This magnetic confinement is why we detect cosmic rays here on Earth. Without the galaxy's magnetic field to corral them, these incredible particles would simply fly off into the intergalactic void, and the universe would be a far less energetic place. The true shape of these magnetic fields is a marvel of cosmic architecture. In many spiral galaxies, observations from radio telescopes reveal a striking large-scale order. The field lines often beautifully trace the galaxy's spiral arms, flowing along the same majestic curves as the lanes of gas, dust, and young stars. This suggests a deep connection between the dynamo process and the density waves that shape the spiral arms themselves. In some galaxies, the field extends far beyond the visible starlight, forming a vast magnetic corona or halo that envelops the entire galaxy. This reveals that the influence of magnetism is not confined to the star-forming disk, but is an integral part of a galaxy's extended atmosphere, a testament to its pervasive power. Unraveling the mysteries of these fields requires looking at the universe in a different light, specifically the light of radio waves. As electrons spiral at near light speed around magnetic field lines, they emit a very specific type of radiation called synchrotron emission. This produces a faint but detectable radio glow that allows astronomers to chart the magnetic universe. By carefully analyzing the polarization and strength of this radio light, they can create detailed maps of magnetic fields in other galaxies, turning an invisible force into a visible map of lines and currents. Each new map brings us closer to understanding how this subtle force helps shape the evolution of galaxies, from the birth of their youngest stars to the journey of their most energetic particles, proving that even the weakest forces can leave the grandest impressions when given cosmic space to play. Yet as we chart these colossal walls and immense voids, a fundamental question emerges from the cosmic data: is there a limit? A point where the universe finally surrenders its clumpy, structured nature and becomes truly smooth and uniform. This brings us to a profound theoretical boundary known as the end of greatness, a scale beyond which the cosmological principle must finally hold sway and no larger structures should exist. It's a cornerstone of our entire understanding of the universe, but the discovery of formations like the Hercules-Corona Borealis Great Wall and the giant arc is putting this concept to the ultimate test. The end of greatness isn't a physical barrier you could crash into. It's a statistical and theoretical horizon. The idea stems directly from the cosmological principle itself, which states that on sufficiently large scales, the universe is homogeneous and isotropic, the same in every direction and uniform in its composition. After the Big Bang, the universe was indeed incredibly smooth, as evidenced by the near-perfect uniformity of the cosmic microwave background, but it wasn't perfectly smooth. Tiny quantum fluctuations, smaller than a single atom, were imprinted on this fabric. Inflation then stretched these microscopic ripples to astronomical sizes, creating the seeds for all future structure. Gravity has spent the last 13.8 billion years amplifying these seeds, pulling matter into the dense regions to form galaxies, clusters, and the filaments of the cosmic web, while the emptier regions expanded into void. The end of greatness is the scale at which this amplification process stops. It's the transition point where the gentle, rolling hills and valleys of the primordial universe have been stretched so wide that they finally flatten out, and the cosmos regains its smooth, average density. For decades, cosmological models placed this transition at around 150 to 300 million light-years. Beyond that scale, we should see no more surprising giants, just a bland, featureless soup of evenly distributed matter. The problem is, our telescopes are now showing us something very different. We are finding structures that are orders of magnitude larger than this theoretical limit. The Hercules-Corona Borealis Great Wall at 10 billion light-years and the giant arc at 3.3 billion light-years aren't just slightly bigger than expected. They are colossal outliers that exist on scales where the universe is supposed to have run out of interesting features. It's as if we've been told that no mountain on Earth can be taller than 1,000 meters, only to somehow discover a range of peaks stretching 50,000 meters into the sky. These aren't just exceptions to the rule, they feel like challenges to the rulebook itself. This creates a serious tension at the heart of cosmology. If these structures are real and their immense size is confirmed, we are faced with two equally dramatic possibilities. The first is that our standard model of cosmology, which includes dark energy and cold dark matter, and has been incredibly successful at explaining a vast range of observations, is somehow incomplete. Perhaps the initial fluctuations from inflation were not as random as we thought, and contained pre-existing patterns or correlations on impossibly large scales. Maybe dark energy or gravity itself behaves differently on these vast distances, allowing structures to form more efficiently than our equations predict. The second, even more radical possibility is that the cosmological principle itself is wrong. What if the universe isn't homogeneous on the largest scales? What if we live in a special place, a region of unusual density, and the greater cosmos beyond our view is fundamentally lumpy and uneven? This would be a Copernican revolution in reverse, dethroning us from our assumed place in an average universe and placing us instead inside a cosmic anomaly. The resolution to this puzzle lies in the delicate art of cosmic cartography and statistics. Detecting these vast structures is incredibly difficult, and their confirmed existence often hinges on complex analysis and the precise boundaries of the surveys used to find them. Some scientists argue that what we perceive as a single, coherent structure could be a chance alignment of several smaller, unrelated filaments seen in projection from our particular vantage point, a classic case of seeing shapes in the clouds. The true test will come from next-generation surveys that will map the universe in even greater depth and volume. Projects like the Dark Energy Spectroscopic Instrument are creating three-dimensional maps of tens of millions of galaxies, allowing us to see the cosmic web in unprecedented detail. These new maps will either solidify the reality of these superstructures or reveal them to be statistical phantoms, mere artifacts of our limited perspective. Whether the end of greatness is a real boundary or a horizon that recedes with every new discovery, its investigation is forcing a thrilling evolution in our cosmic philosophy. We are being compelled to ask not just what the largest structure is, but what the word structure even means in an infinite or near-infinite universe. The search for this limit is ultimately a search for understanding the universe's true personality. Is it fundamentally orderly and predictable, or is it capable of wild, unexpected flourishes that defy our best models? Each new giant we find, whether confirmed or debunked, teaches us more about the powerful forces of gravity and dark energy that have been wrestling for control of the cosmos since the very beginning. From the staggering scale of the Hercules-Corona Borealis Great Wall that defies the cosmological principle, to the haunting perfection of Hoag's object, a galaxy that looks less like a natural formation and more like a celestial fingerprint. We've journeyed through a universe that constantly refuses to play by the rules we write for it. We've stood at the edge of the Boötes void, a sphere of nothingness so vast it could swallow thousands of galaxies, and we've looked up at the Fermi Bubbles, colossal structures towering over our own Milky Way that we somehow missed until just over a decade ago. We've traced the Magellanic Stream, a river of stolen gas revealing a dark matter secret, and felt the repulsive push of the local void, an emptiness so powerful it's shoving our entire galactic neighborhood. We've mapped the invisible dark matter halos that form the true backbone of the cosmos and grappled with the giant arc, a structure so large its very existence seems to bend the laws of physics. We've found our address within the continent of galaxies known as the Laniakea Supercluster and pondered the CMB Cold Spot, a chilling anomaly in the afterglow of the Big Bang that just might be a bruise from a collision with another universe. We've witnessed the explosive fury of radio galaxies and tried to comprehend the billion light-year architecture of the Pisces-Cetus complex. We've seen how the humble galactic bar acts as an engine for creation and destruction, and debated the existence of the KBC void, a proposed cosmic bubble that could solve the Hubble tension and redefine our local place in space. We've been pulled by the mysterious drift of dark flow, likely toward something immense beyond the horizon of our observable universe, and we've seen how the disks of galaxies like our own are warped and bent by unseen forces. We've tried to use the Eridanus supervoid to explain a cosmic cold spot and failed, and we've fought to see through our own galaxy's zone of avoidance, a blind spot hiding entire superclusters. We've identified the fossilized remains of galaxies consumed by our own Milky Way and followed the gravitational trail to the Great Attractor, a hidden focal point pulling us toward an unseen mass. We've hunted for dark galaxies like Dragonfly 44, ghostly halos of matter that forgot to form stars, and we've paid homage to the CFA2 Great Wall, the pioneer that first revealed the universe's large-scale structure. We've traced the delicate threads of galactic magnetic fields, invisible forces guiding cosmic rays and star birth, and we've questioned the theoretical end of greatness itself, wondering if there is any limit to how large cosmic structures can become. Each of these 25 structures is more than a celestial curiosity. It is a direct challenge, a question mark etched into the fabric of reality that pushes the entire field of astrophysics and cosmology forward. They force us to refine our theories, to invent new technologies, and to remain humble in the face of a universe that is infinitely more complex and wondrous than we can often conceive. And this is just the beginning. With the James Webb Space Telescope peering deeper into the infrared universe, the Vera Rubin Observatory preparing to scan the entire sky every few nights, and new gravitational wave detectors coming online, we are on the verge of a new golden age of discovery. What even more astonishing formations lie waiting in the darkness? Will we find structures that make the Great Wall look small? Could we finally uncover the true nature of dark matter or glimpse direct evidence for a multiverse? The greatest cosmic mysteries are still out there, waiting for the next curious mind to uncover them. So tell us in the comments which of these galactic enigmas captures your imagination the most. Is it the haunting emptiness of the voids, the impossible scale of the walls, or the ghostly whisper of dark matter? Let us know, and be sure to subscribe so you don't miss our next journey to the edge of understanding.